Welcome to this video. We're going to derive Newton's law of universal gravitation, which says that any two objects in the universe pull on each other with the force of gravity. But first, imagine you're walking down the road. A car is zooming by and your friend is concerned for your safety. Here it is from above. The road looks like that, there comes the car, and you're moving this way. How does your friend turn you away from the road? Well, if she tries to push you this way, you'll just speed up. If she tries to push you this way, you'll just slow down. But if she pulls you this way, you'll turn. In order for something to turn, requires that there be a force directed perpendicular to the velocity. This arrow and that arrow are at 90 degrees. Here's another example of something that's turning, a planet. Imagine the planet's just hurling off in this direction. It's moving really fast, and Newton's first law says it's not going to slow down or speed up, and it's not going to turn unless there's an unbalanced force pulling it. So if the force pulls it perpendicularly, it'll turn. What do planets turn around? They turn around a sun or a star. Now this planet has some radius for its orbit. We call that the orbital radius. And the time it takes to make one revolution to go around once, that's called the orbital period, capital T. If you take this planet, and let's say it's the Earth, if you take the orbital period squared and you divide by the radius cubed, then for the Earth you have 365.2 days divided by 150 million kilometers roughly, and you make that cubed, you get 0.040. Now let's take a different planet like Venus. It has a different radius, a different orbital radius, and a different orbital period to go around once. But if you take t squared over r cubed, here are the values for Venus, and what do you get? 0.040. In fact, it doesn't matter what planet you choose. It could be as far out or as close as you like. No matter what planet you choose, the orbital period squared divided by the orbital radius cubed always equals the same constant value. That was pretty puzzling to scientists back in the 1600s, and after all, they didn't even know what was pulling on planets to make them turn, until Newton came along. Imagine you take an apple and you let it fall. Why does it go down? Because gravity pulls it down. Newton said that the total force on an object is equal to its mass times its acceleration. In this case, the total force is just the gravity force. Nothing else pulls. The object's mass we'll call little m. And its acceleration, we've learned that no matter what you drop near the surface of the Earth, if it's an apple or a banana or a watermelon, the acceleration is always 9.81 meters per second squared. And we call that value little g. Little g is a constant. It doesn't change for different objects. But even though this is a constant, the gravity force is not the same for different objects. A watermelon is heavier and has a bigger gravity force than an apple. That gravity force depends only upon the mass of the object, because little g is fixed, and it's the same for all objects. So what we do is we write a proportionality like this, which takes away anything that's constant, and it shows only the things that can change to impact the value of Fg. This is a really important proportionality. It says that the gravity force pulling on an object is proportional to the object's mass. The gravity force here pulling on the apple is proportional to the apple's mass. And if this were a watermelon, the gravity force pulling on the watermelon would be proportional to the watermelon's mass. We're going to use this later, so we're going to put a blue box around it, and remember, the blue box means we've seen that before. Now when you drop the apple, what are you standing on? The Earth. If you drop the apple from here, it's pulled this way. If you drop the apple from here, it's pulled that way. So what's actually pulling on the apple? And we don't want to say gravity, we want to be more specific. What's pulling on the apple? It's the Earth itself that pulls the apple. And we can see that because of where the apple is getting pulled. It must be the Earth pulling. Let's write that down. The apple is pulled by the earth. Newton's third law says if you have two objects, A and B, and if A is pulled by B with a force F, then B is pulled by A with a force F. In this case, what are objects A and B? Apple and earth. If the apple is pulled by the earth with a force, Fg, then the earth is pulled by the apple with a force, Fg. You just switch the order of the two. Wait a second. The earth is being pulled? That's what this says. And in fact, not only does the apple pull on the earth, but the person pulls on the earth too. How do we know? Because the earth pulls on the person. Now, we said earlier that the gravity force pulling on an object is proportional to the object's mass. So, the gravity force pulling on the apple is proportional to the apple's mass. And the gravity force pulling on the earth must be proportional to the earth's mass. And we'll call the earth's mass big M. That's pretty weird, because look at this. The two gravity forces are the same according to Newton's third law. That means the gravity force on the apple is proportional to the apple's mass, and that same force is proportional to the Earth's mass. The gravity force pulling on the person is proportional to her mass, and her gravity force is proportional to the Earth's mass. We're almost ready to put this all together. Imagine you're sitting under an apple tree, and the apple at the very top is about to come loose. If it does, it'll be pulled down by gravity. And then you look over and you see another apple tree twice as high. There's an apple at the top, and you think to yourself, if that apple comes loose, it'll be pulled down by gravity too. And then you look, and the next thing you see is the moon, with its mass little m. And you think to yourself, if gravity can reach all the way up to the highest apple tree, maybe gravity can reach all the way up to the moon and pull on the moon too. That's really important because remember what the moon is doing? It's turning. Something has to be pulling the moon toward the middle of its path. Newton said maybe the thing pulling on the moon is the gravity force. Another way to express this is like an equation. Here's the equation for Newton's brilliant idea. It says the gravity force is what provides the net centripetal force, pulling the moon toward the center of its circle. The net centripetal force on the right side, well, we know that formula. It's mass times speed squared over the radius. Now we can take speed and plug in distance over time. In one orbital period, when we go around once, how far do we travel? The circumference, 2 pi r. If we distribute the squared to everything in parentheses, the 2, the pi, the r, and the t, and then we simplify the r's, we get this. Now watch what happens when we multiply both sides by t squared over r. The t squareds cancel, the r's cancel, and we're left with just 4 pi squared m. And on the left side, look at what we have. It's almost Kepler's third law. You have t squared, you have a constant over here, but we're missing the r cubed. Right now we just have a single r. So when we plug in for gravity, we're going to have to put 1 over r squared because you need an r squared to combine with this r to make Kepler's third law. Now, what about the numerator? We know what's in the denominator. Well, if the numerator is a 4, then the 4's will cancel. If the numerator is a 3, we can just move it to the right side with the other constants. No matter what the numerator is, the point is it has to be some constant, which combines on the right with these constants. The important fact is that the force of gravity has to be some constant divided by r squared. Why? Because that r squared combines with this r to make Kepler's third law. And so Newton said that force of gravity is proportional to the inverse of r squared. When we take these three things together, we can put them into one single proportionality. The force of gravity on an object like an apple is proportional to the apple's mass times the Earth's mass, divided by the distance between them squared. But Newton looked at this equation and said, you know what? This isn't just true for apples. It's true for watermelons and for bananas and anything else on the Earth. But it's not even true just at the Earth. It's true for objects that orbit the Sun, like Mercury and Venus and Earth. All of those planets are moving in orbit, and so they must feel gravity forces too. And by the end of that thought, Newton said, maybe this equation is true for any two masses that are separated by some distance r. For any two masses in the universe, each one feels an attractive gravity force, which is proportional as given by this equation. This is a pretty wild and bold statement. Right now, as you watch this video, your nose is being pulled by the monitor. Why? Because both objects, your nose and the monitor, have mass, and gravity acts between mass. Right now, the wall that you're in the room that you're standing in, the wall is pulling on your left hand. How do we know? Because both objects have mass, and gravity acts between mass. This formula, Newton said, applies to any two masses in the entire universe. And this is Newton's law of universal gravitation. And we've seen that the way to derive it is by deriving each constituent proportionality.